So this is test number 5. You have only sections 4.1, 4.2, 4.3, 4.5, and 4.6. 4.1 and 4.2 we did together as one main section. 4.4 we didn't even include, but we did include stuff from 4.4 in 4.5. If you remember, 4.4 was about greatest common factor, least common multiple, those terms. The test itself will be 35 points only, I can tell you right now. Okay, I just actually finished making it last period. So it's a bit shorter than the last one. I think the last one, what was it? Do anyone have it handy? Was it 40 points?
It was 45.
45? So it's a little bit shorter than the last one, all right? Which means it weighs a little bit less, but it still has a huge significant part of your grade at the end of the quarter, right? Think about the quarter, it's 60% test, yeah.
Does this mean that it'll be a shorter test in terms of
yes.
So
In,
we'll finish
in length and in material we've covered, it's been shorter. Because remember, we spent 3 days on the quarter 2 project. So that's the reason why this one is a little bit shorter than the previous test. 3 class periods we spent on a project, so it's going to be less. Hey, something I should mention, I mean, not that it matters right now, but on the midterm, we're going to be like a section or 2 behind the other freshman class, which is fine because we do projects during the quarter. You're going to have a couple questions on the midterm about the projects. So don't let those just forget, fall out of your mind. So the stuff we did with the first quarter project with multi-criteria decision making, I could ask you some sort of a conceptual question. I'm not going to have you do a whole project of that on the test, right? But I could ask you questions about that. The second quarter project with optimization, the idea of using the inequalities to find the corner points and stuff, those kind of questions could definitely appear on the midterm and will appear in the midterm. So just keep that in mind as you're studying for the midterm. I'm going to give you a review packet next week, or at the end of this week. Okay, it's something that you can work on over Christmas break if you want to. It's not collected, it's just practice for you to practice before the midterm.
I think for our review, we feel mostly go over technicalities of how exponents and just technicalities, kind of the trick questions.
Okay, I can go over stuff with the rules of exponents. Is that what you mean?
Can we go over
Sure.
The squares,
And factoring questions?
the cubes as well.
Cubes, like factoring with cubes. All right, so let's jot those 3 things down real quick so we read them all. So we got exponent rules, general factoring, and specifically asked about was cubes. What other stuff do you want to go over? I'll make questions for these, but if there's stuff that you're thinking of right now that you want to make sure we get to, just give me the topics and we could go one at a time through each.
There was one factoring problem. It was kind of strange. I felt like reading it over. It was just
Can you find it?
Squares. Yeah, I'm trying to find
All
it
right.
now.
Find it and then just read it to me. So let me start with, Hannah again.
There was one of them where it was the 2 binomials and it equals a polynomial, and then you figure it out.
A, B, and C.
Yeah.
Oh, yeah, that one.
Equating coefficients.
Yeah. Something.
That was in 4.2 or 4.1, I think. I don't have the text in front of me, but it was 4.2 or 4.1. I forget which section. God bless you. There were a couple example problems in your test. 4.3, was it? Okay. So equating coefficients was with A, B, and C, and you have to determine those values. All right, so let's start with exponent rules. Let's do an example of that. Okay? What I'm going to try and do is make one so complex that it involves all the rules at once. That make sense? Okay, I'll make it very complicated on purpose. So let's say we've got the following. Let's say we've got x squared, y to the third, z to the 0, w to the 4th, all squared, times 2x, y to the 2nd, w squared, all to the 3rd.
Could you do that thing where you multiply into the parentheses, 2x outside the parentheses?
Sure. So let's do it if you want to make it a little more complicated than even that. Well, let me make it a second problem if you don't mind, because it's gonna make this one's insane. So let's start with our rules first. How would you start this problem? And there is only one way to start it. There's no multiple answers to this. There's only one way to start this problem. Okay, any other way would not work for you. There's one way to always start this one. What do you think?
Start putting the exponents in for each of the variables and multiplying the 2 exponents.
So I need more clarity.
4, 5, 6.
All right, so distribute or
Yeah.
reason out the exponent on the outside. I would agree. I would start with this exponent on the outside. Why can't I just start by doing this? Because I see I have x squared here times x here. Why isn't that just x to the third? How come I can't just work the insides first? Why can't I work the insides first? Very good.
Because in PEMDAS, exponents comes before multiplication.
Exponents come before multiplication. Simple enough. So we take care of our exponents. As Tristan mentioned now, look, you have squared, squared. That means it's to the fourth because you need to do what to those powers? What do you do to the powers? Multiply them. So y cubed squared is y to the sixth. In case some of you are forgetting this still, think of this as y cubed times y cubed. Right? Y cubed times y cubed. That's what squared means here. So y cubed times y cubed is indeed y to the sixth.
No, it's
Sure. How about next? Z to the 0. George? 2?
Yeah.
Z to the 0 is really 1. Okay. I was like, where are you getting 2 from? Yeah. Z to the 0 is really 1. And then 1 squared is still 1. So anytime you see something to the 0, what do? Yeah, does it have any effect on the problem actually though? No. Okay, because we're multiplying. If the problem had something like this, where it was all this work, right, it was a bunch of gibberish, whatever, and then it was plus x to the 0, then it matters because this becomes plus 1 at the end, right? Anything to the 0 is 1. But when it's multiplied by several other things, like in here, if I put a 1 here and multiply it, these all remain the same. So this doesn't no effect. Yeah, I could really just go like this. If you want to put a 1 in its place, you can, but it has no effect on the answer. If, again, it were alone, right, if its own term by itself, you got to put a plus 1 at the end. This x to the 0 becomes plus 1. Yeah, but in this case, we have it multiplying, not adding separately. W to the fourth to the second, Bridge, what do you get? W to the eighth. Times. Annette, what do I get on this side? How do I start that off? How do I begin this part here?
So you would multiply 2x by 3. So you basically said have up 8 x to the third, y to the sixth, w to the sixth. You multiply the exponents.
Good. And how did you get the 8? That was the only one that was a little different.
So basically you're just cubing 2.
Mm-hmm. 2 times 2 times 2 gives you 8. Everything else multiplied by the exponents. Now that we're in this scenario, and it looks like, oh, I left the parentheses here, but didn't leave them here. Does it matter? Why not? Yeehaw. Right away you shook your head no. Parentheses doesn't matter here. Why? Everything's multiplying. Is that clear? Don't fall into the case where you think because it's parentheses you have to start distributing and stuff. It's all multiplication. When you multiply things with the same bases, what do you do to the exponents? When you multiply two things, for example this and this, that have x as the base, the same base, what do you do to the exponents? Yeah, sum them together. So x to the fourth times x to the third, x to the seventh. What's in front of this x really right here? What is it?
1.
And 1 times 8, it remains 8. So that carries in front. Then I've got y to the sixth times y to the sixth. Oh, that's y to the 12th. And then finally, w to the 8th, w to the 6th is w to the 14th. Okay, I'm going to give you 2 more variations of problems with exponents. That's one variation. Okay, that's one variation. Let's go to a second variation for exponent problems. Let me just remember, factoring and equating coefficients. Don't let me forget those topics next. So let's say we've got w to the 2x plus 1 times w to the 3x plus w to the 8x minus 2. I've got a problem like this that says simplify the expression, or it could say perform the indicated operation. Either of those directions would work in this case. What's the first thing you think about when you start a problem like this? What's the first thing you think about?
You want to distribute the w to the power of 2x plus 1 to the each w. So you add the 2 exponents.
Why do you add the exponents? How come?
Because both w, like the same.
What's the word for that?
I forget.
W?
Variable? Is the
That
right
works,
word?
but base is the word we're looking at right now.
Yes.
Good. So right away, Luke recognizes that W is the base amongst all things. So when distributing this to this, these have the same bases, and the rule of thumb the rule that we know is to add the exponents when multiplying things with the same base. I'm writing it out in the second line. See what I did there? You don't have to do this step if you don't want to. Okay, you don't have to show this step every time. The reason I'm showing this step is to recognize that this is multiplying by both of these terms. As a result, if I add these exponents, I'm going to have 2x plus 1 plus 3x. Combine like terms, please. It's just 5x plus 1. Please be careful. Do not distribute this 3x to both of these. That's the common mistake I would see there. Again, if you were to multiply exponents, you would take the 3x and distribute it to both. But we're not multiplying exponents. We're multiplying these overall factors. And when multiplying factors with the same base, we need to remember to add the exponents.
So if the W wasn't there, then they'd be multiplying.
If the W wasn't there, yeah, I mean, but then it would just be multiplication of a polynomial, correct? If these were the actual bases, 2x plus 1 times 3x, sure. Over here, the same thing. Let's add the exponents again. I carry down my plus sign. Notice my plus sign started here. It carries down, it carries down. What if this had been a minus sign? It would carry down as a negative sign the whole way through. Then I take 2x plus 1 and add 8x minus 2, giving me, what is that, 10x and then a minus 1? Now, it's really tempting to go further, isn't it? Like, this jumps out at you and says, like, come on, add me together. Let's go ahead, do it. Why not? Why not?
You can't, because they're different,
Different what?
different terms. The
Yeah,
exponents.
because
Yeah.
if it was multiplication, you could have combined them together, but because it's addition, it's like almost like it's all together.
Yes, that's exactly right. These are not like terms. Had this been multiplication, sure, if there's a multiplication sign, we'd add together those exponents and we're done. But this is not multiplication. This is addition. I know. And as a result, because this is addition right here, we have to remember that for this problem, these are two separate terms. This is like having x and this is like having y. It's like saying x plus y. Can you combine those two? No, you can't. Okay, or it's like saying this, and this is what some people think of to make it easier. Think of these as like x squared plus x cubed. Sure, the bases are both w, right? The bases are the same, so these bases are the same, but are these like terms? No, because the exponents are different. These are analogous to one another. Okay, again, this is treated the same way as this is treated. Let's go to that last type of exponent problem you could expect. And I spoke about this a little bit. You had one homework problem on this, and I mentioned it, and you could definitely expect it on your test. So let's say we had something such as, I'm trying to think of one that's interesting. Let's say we've got this. How about that? Solve for x. First of all, why is this an exponent problem? Why is this one of those exponent problems? Why does it fall into that category? You gotta speak a little bit louder, George, and clear.
They're both like square roots and they have exponents. So
Okay, they have exponents. They're both cubes or squares of other things. Agreed. Agreed. But what can I make it look like to make it more obvious? What could I do to this? What's the first step I could start with? Hannah, what do you think?
you can make the bases equal to each other.
Yeah, so let's write a little note if you didn't know that. Try to get the bases equal to each other here. Whenever the exponent has a variable in it, get the bases the same. Again, look at the exponent. See the variable in the exponent? As soon as you see a variable in the exponent, you need to equate the bases somehow. So what's 25 really? If I think about it as a function of powers, we're looking at powers here.
5 squared.
It's 5 squared. And what's 125 really? What's 125, yeah? It's 5 cubed. Okay, I'm not going to ask you to have to know all of these, but you should know some of the basic ones. You should know 1 squared, 2 squared, 2 cubed, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the fourth, 16 to the 5th, 32. Just keep doubling. You should know 3. 3 squared, 3 cubed. 4. 4 squared, 4 cubed. 5. 5 squared, 5 cubed. At least you should know all those. Okay, I allow you to use your calculator on the test, but honestly, it takes more time than to sit there and figure it out, doesn't it? You should know those numbers by now. Okay, think about your cubes up to at least 5. You should know all of your cubes up 1 through 5 at a minimum. For 2, you should know even more, like 2 to the 4th, 2 to the 5th, you should know those. I'm not going to really have you memorize like 3 to the 6th or something like that, you know, where you could just figure it out. Okay, but certain numbers you should kind of know. That's how I would start this. Now, what's my rule? What rule do I apply at this point? Somebody besides Hannah, she started this off. What rule at this point do I apply? There's a rule that's applicable here. Yeah, Max. Max, wow. Tristan, go for it.
You multiply exponents.
Multiply exponents, good. Sorry, guys.
You go 5, 6x.
Good.
And then you go 5, and then you go 6x minus 21.
Good. Notice, Tristan remembered that when you multiply a power by another power here, when you're raising them, you need to distribute this power to both because you're technically multiplying. If I were to multiply 3 times the quantity 2x minus 7, I need to distribute that 3 to both of those. Why is it? Oh, this is annoying. I did this again. Remember last class I did this? Or didn't I do this one other time with you guys?
Yeah.
So what would the answer actually be in this case?
Well, wouldn't you turn 6x and 6x minus 21 into one equation?
Yeah, you would set them equal. What's the problem that I just realized? That's why I laughed a little bit. What did I screw up here? I picked random numbers, obviously. George?
You're gonna have it does not, 0 does not equal 1.
Yeah, you're going to get 0 equals negative 21, which is not true. So this is a contradiction. So there is no solution. Okay, that's this example. But you understand the process? Okay? You get to the point where the bases are absolutely identical. And then once that's the case, you equate exponents. And equate exponents. You could call this equating exponents as a topic if you'd like to. And you're equating the exponents. In this case, there'd be no solution. It's fine that we have this example. That's totally fine. You could have no solution, right? You could definitely have no solution as the answer to this. That works. Questions. What if I got something that said 15 equals 15 as my final answer? What if I got 15 equals 15 as my final answer?
All real numbers?
Yes, any number would work. Agreed? Okay, any number would work. All right, that's the gist of exponents that you should know. Let's get into factoring and then that question on equating coefficients with A, B, and C and that kind of stuff. Okay, so let's start. Let's write down the following. Let's say we've got ax squared plus 2x minus 4 plus 3x squared minus bx plus 2 equals, let's say for this one, 4x squared plus 5x minus c. So use the idea of equating coefficients here. Try to recognize right away that on both sides of the equation, you've got something squared, something linear, something constant. Those three things. Squared, linear, constant. So Hannah, did you pose this question earlier? So Hannah asked the question earlier about this, so we review for the test here. Can somebody step me through what we'd go through for this problem? How would you approach this? What do you think? Approach it.
Well, you could distribute the positive sign, and then you could try to, like, if you have like ax squared, and then you find like, and you have 3x squared, then you make it using like 4x squared, like, so that way it equals, and you find it.
Yeah, so George is seeing that he's got like terms here, and he's got to think about these like terms as being paired up with this first term right here. Think about all the things with x squared to start. So what's ax squared plus 3x squared? How do I write that? How do I write ax squared plus 3x squared? For example, let's say hypothetically that instead of being ax squared, this was a 2, okay? If this is a 2, it's 2x squared plus 3x squared. What would that give me? 5x squared. So what did you do to the coefficients? You added them, right? But now your coefficient is a and 3, so what should you do to those two coefficients?
Add them.
Add them. So this first term is going to be a plus 3x squared. I need you to really stop and think about this for a second. Replace a with a number and think about what you would do. If a, I just went over this, but if a was a number like 2 or 3 or 4 or 5, you would take that expression and add it to this expression by adding a coefficient. That's how you would do it. This is the exact same answer. Plug in a number for a. Plug in a 4 for a. 4 plus 3 would give you a 7. Look, 4 plus 3, that would give you 7, wouldn't it? So the way I'm writing it is absolutely true. It's just not necessarily the most simple way to express it, or the way you would traditionally see it, because usually the coefficients are numbers. Now I'm giving you little parameters. How about the middle term? What's 2x minus bx, or plus negative bx? How would I write that? What do you got, Bridge?
Would be in parentheses 2 minus b, and then outside the parentheses.
Very good, Bridge. So he's picking up on the pattern, right? I'm hoping we're all picking up on this pattern here. Now, whatever you would do if it was numbers, you would do with variables. This would normally be a 2 here minus whatever that number is. Well, that's right here, 2 minus b. And last but not least, the last part is important still. George? Bless you.
2 plus 1, or no, 2 minus 1, and then I would negative 2
Yeah, so just combine them total. What do you get?
You get
Negative 2. Very good. That last one, because it's constants, we don't have to worry as much about it being difficult. And now on the left-hand side, we simply carry down what we had. Luke, what's A? By inspection, just by looking.
1.
It's 1. Does everybody see that? I want you to see it just by looking. Forget writing anything down at this point. Look at the equation. Can everybody see that A must be 1? Plug in a 1 for A. What do you get here?
4x squared.
And what do you have here? Do you see how those are equal? Hence equating coefficients. So A is definitely 1. A is definitely 1. Tristan, what's B? This one's a little tougher.
B is
Close. Very close. It's not 7. Not negative 3. Oh, sorry. Yes, negative 3. Why was 7 close? What would you get if you plugged 7 in, Tristan? What's 2 minus 7?
oh, it's negative.
It's negative 5. You wanted
Positive.
positive 5. So negative 3 equals 2 minus negative 3 gives you 5. If you weren't sure of this, by looking, what do? If you're not certain by looking, you write the following, please. You take this coefficient right here and set it equal to this coefficient right here. You say 2 minus b has to equal 5. The only thing that b could be to make this work is negative 3. And then finally C. Be careful with this one. I can see a lot of mistakes on this one accidentally. C? What is it? Yeah, just 2. Be careful. Okay, why is it just 2? Because you got negative 2 and negative C. Look at the original. This is a negative 2 here. This is a negative C over here. So as a result, C must be 2. Okay, does everybody see what I'm talking about here? The negative signs, you would say, and the next line, you would say negative 2 equals negative C. So C equals positive 2. Now, after this, it was all just factoring. So I'm just going to go through a bunch of problems. Is that reasonable for factoring? We'll go over all the different techniques and possibilities. Questions so far? All right. Before I do any factoring, what's step 1 of all factoring problems? All factoring problems, what's step 1? Doesn't matter what it looks like.
So you can actually do.
Yeah, GCF. So let's jot that down in case we forget. Okay, step 1 is always GCF. Now, once you take out a GCF, you got several options here. You could see something that has sum or difference of cubes. That's a special factoring technique. We could have difference of squares. We could use AC method. We could use just regular grouping. Remember, AC method has grouping in it. So we do AC method, then we do grouping. We could actually use what's called, if you remember, the square of sums or differences. And then finally, just regular factoring of quadratics. Those are all the different types of factoring we've done, actually. We did a lot. We didn't necessarily do them in that order. It doesn't matter what order we did them in. I just want you to see that we did all of these. So remember, AC method involved grouping, then there was regular grouping. There was something where it was like x plus 2 quantity squared. We had that as an option. We did regular factoring of quadratics, meaning there was no one value, but the a value was 1. Difference of squares, sum of cubes, difference of cubes, did all that. So, I don't know, you want to go from hardest to easiest to mix things up a little bit, or what do you think is the hardest out of all these?
I was a little confused by the AC method.
AC method is a little tough. You want to start with one of those?
That's my favorite.
Yeah.
It's your favorite? All right, I like AC method. Let's take a look at that to start. Okay, let me give you a good example of this. Hey, by the way, how do I come up with great examples? Seriously, how do I come up with great examples for AC method? How do I know it's going to work? Max? Say again? Yeah, but how do I know that it's definitely going to work? Like, what am I doing right now? Yeah, I'm actually multiplying 2 factors right now on the computer and coming up with an overall trinomial. So when you're working on this, if you want to work on practicing problems like AC method and you don't know what problems to use as examples, just multiply out 2 binomials, get your answer, and then try to factor it back out. You follow what I'm saying? So I'm choosing two variables or 2 factors that are numbers like 2x plus 7 and 5x minus 4. Multiply those 2 things together, you'll get an answer, and then you got to refactor it to see if you practice. So let's do the following one. Let's say 6x squared, so this is AC method, 6x squared minus 23x plus 20. Since it was George's favorite, let's see if George remembers how to start it. What do we start with, George?
You know, 6 times 20, you get 120, and then you find that you're gonna get like the factors of it that add up to a mix of what gets you -23.
Okay, so meaning factors of 120 that add up to -23. Very good. Can anybody tell me what those factors might be? What are some factors of 120? Give me a couple, not just 1 or 2. Give me a bunch of them. We'll see which one. Ash? Of 120, not 20. Of 120.
4 and 30.
4 and 30, that works. What else, Tristan? 12 and 10. What else? So far, any of these work? What else?
16 and
6 and 20?
2. 60, yeah, I don't.
Or, go ahead, 60 and 2.
Yeah.
George?
5 and 24.
5 and 24. Annette?
30 and 40.
30 and...
40.
We have 30 and 4 already.
Oh, no, it's like 4 and 30. I mean, 3 and 40.
There you go. 3 and 40. I'm missing one. Are we missing one, actually? Do any of these somehow give you 23 when added?
Oh, yeah, 15 and 8.
There we go. That's why I knew we were missing one, because none of these worked. You see that, guys?
15 and 8, yes.
Think about all of these options. And let's pause for a second, actually. actually discuss something, because I think this is a little misleading. See the middle term? Middle term, its sign is negative, right? So the two numbers that we're adding together have to both be negative to add up to a negative. Or one can be negative, one can be positive, right? Or they can both be positive. But if they're both positive, you add two positives, you'd end up with a positive. So that wouldn't work. If one of them was positive and one of them was negative, that could add up to a negative, but would that multiply to give you a positive? Like if I made this positive and this negative, do these two multiply to give me positive 120? No, because one would be positive, one would be negative. So because this is positive and this is negative, these must both be what? Negatives. So all of these answer choices have to all be negatives, no matter what. So I'm listing down the factors. I'm not listing positives or negatives, though. But if I think about this, I could see that negative 15 and negative 8, now that multiplies to positive 120, which is what we're looking for right here. And negative 15 and negative 8 adds up to negative 23. So remember, those are not my answers for AC method. For AC method, these are just the things that you break up the middle term into. So as a result, we get the following. In the middle terms, remember, are what we just wrote down. The 15 and the 8. Another common mistake I see all the time. I see people, oh, it's negative, sorry. I see people put there we go. I see students place these values in here without the x. That happens a lot. Because here, negative 15 and negative 8, they don't have x's next to them, right? So I see all the time copying down negative 15 and negative 8 without the linear part, without the x. Okay, please don't forget the x there. Now, I can treat this problem and factor it by what method? How do I factor a problem that has 4 terms? What's the indicating thing? When you see 4 terms, Max, what do you think? Grouping. As soon as you see 4 terms, think grouping. Okay, if you need to do that, put a little dashed line down the middle like we did there. What comes out of 6x squared minus 15x? What comes out of there?
Outside the parentheses is 3x, and then inside the parentheses is 2x minus 5.
How do you know the bridge is right? How would you know that you're right when your answer is here, George?
You just bring over what's in parentheses and then
So the 2x minus 5, what about it then, George? Where does that show up again?
that shows up after
So what's the number that's going to be pulled out then?
4.
4?
Yeah.
You sure?
Negative 4.
There you go. You need to take out a negative 4. Because a negative 4 coming out of negative 8x is what gives you the 2x. And a negative 4 coming out of 20 is what gives you the negative 5 right here. Tristan, what's common? What's common in both terms?
They both are factored out and become 2x minus 5. So you can group the 3x minus 4 with 2x minus 5 and get your answer.
Okay? So recognize that 2x minus 5 is in both terms now. You went from having 4 terms to when you grouped it, now you have how many terms? You have 1, 2, 3, 4. Now how many do you have?
Now you have 2.
Only 2 terms in this line. How do you know it's only 2 terms? This is one term. This is another term right here. 2 terms, both including 2x minus 5. Take the 2x minus 5 out front. You're left with 3x minus 4. Okay? So again, when you're practicing your problems, what I just did, just so you know, I typed this right into the computer and had it calculate the trinomial, and that's what I gave you the answer to start with. So when you're practicing at home tonight, you can literally just pick 2 binomials, make them a little bit complicated, like 2x minus 5 and 5x plus 2, something like that. Multiply it all out by hand so you can practice multiplication, because that's in this test also, and then refactor it. So by multiplying it out and then refactoring and covering, kill 2 birds with 1 stone, right? Practice your multiplication, practice your factoring. So a hand pop up for instance, yeah.
For on the problem sets, I did this and I got it was for the 2x minus 5 times
I would write that as 2x minus 5 quantity squared.
Okay.
It's the same thing as writing it twice, it doesn't matter. It's just abbreviated nicely by putting it squared. Like if you have 2x minus 5, 2x minus 5, 2x minus 5, 2x minus 5 is your answer, that's 2x minus 5 to the fourth power. However many times it repeats.
Some of the factoring problems, like I can just do it mentally. Is that gonna be like acceptable or should I?
If it's a problem that you can do, for example, let's get to those. We're going to do a couple more still, okay? So I'll get to a few where like you should be able to like almost just look at it and see what the answer is. Are we good on AC method, the idea? You got to practice this. It makes it a lot easier when you practice it, okay? Definitely practice. Let's go back up real quick. I just want to see what the other topics were. Sorry. I know you're still probably writing, but I want to see what these others were. All right. So we've got AC method, check. We got that done. And by default, we did grouping with AC method. We can do that again if you want, but it looks like we covered both of those too. What do you want to go to next? So what you're talking about, by the way, Tristan, is this one and this one we should be able to do by just looking at. Dots and regular factoring we can do by just looking. This one, almost by looking actually too. Some in different cubes, you got to do a little bit of work to show.
We're not like guessing. We should be doing that.
You're not guessing, no. You're not guessing with this. You're doing it with like actual reason to it. George.
I remember the equation like a cubed minus b cubed. Like,
You don't remember it?
no, I do. Like,
Okay.
What do you use that for?
Okay, so let's do that next, okay? So let's go sum and difference of cubes. So we have a formula as follows. Okay, that's our formula. Now, let's start first by looking at the formula and talking about what it means. A and B are the bases of perfect cubes, if you have perfect cubes in your problem. Once you identify what A and B are, all you need to do is take them and plug them into this formula. Now, the plus or minus and the minus or plus. It's really annoying to memorize two formulas. That's why it's written as one formula. But if you wanted to, you can write this twice as plus and as minus. Now, the simple thing to know is when it's plus, this remains plus. When it's minus, this remains minus. So far, so good? Now, after that, you have pretty much the same formula. These are both pluses over here at the end. All the square terms are all pluses. And then the middle term is the opposite of what you started with. So if this was plus, this becomes minus. This was minus, this becomes plus. That's what this symbol here indicates. This tells you when this is plus, use a minus. When this is minus, use a plus. What kind of an example? Somebody give me an example that we could use for sum or difference of cubes. And you should be able to figure out your own. Come up with your own example. It's not hard to do this. Give me an example of something that we could factor using this. Make it a little bit tough. You want to do plus or minus? Okay. Minus 8. That's a perfect example. How come I know that that's a good example? Who can tell me why that's a good example right off the bat?
It's all cubes.
They're all perfect cubes. 27, 8, and x cubed are all perfect cubes. So step one of this is always to identify your bases. What are your bases? So for example, I want you to rewrite this as perfect cubes and figure out what those bases are. George, what's cubed to give you 8?
8
And what's cubed to give you 27x cubed?
3x.
3x. Let's make this even tougher. Instead of x cubed, let's make it x to the 9th. Now what goes in here? Instead of 3x, what should this really be if this is to the 9th? Anna?
3x and a
3x to the 3rd, that whole thing cubed. How do I know that? What's my rule tell me? My rule tells me, yeah, 3 times 3 gives you 9. Remember, a power to a power, you need to multiply those powers. That's where the 9 comes from, and then 3 cubed gives you 27. Yeah? So what's A and what's B as a result? that's the question at hand, really. What is A and what is B from these two? Luke?
A is 3x cubed and B is 2.
Yes, very good. Please, B is not negative 2. B is not negative 2. B is just 2. The negative, yeah, that'll carry over in my formula already. So, George, you start with this question, right?
Yeah.
All right. So, at this point, you know A and you know B. And you're told that this right here, this expression, will always factor into this. And you have this expression right here. That's what you've got. So all you need to do is take the A and B values and plug them in to the corresponding locations. So it's A minus B. So it's 3x cubed minus 2. That's the starting. So I've plugged into there already, so that's good. And now I've got to plug in over here. This is going to be 3x cubed squared plus 3x cubed times 2 plus 2 squared. Does everybody see why this is a plus sign here? Comes right out of the formula. Plus sign, minus sign, minus sign. The last step is to simplify, but you will never be able to factor further. Okay, assuming everything is simplified ahead of time, you've taken out any GCFs. Luke, what do you got?
Okay.
Question?
No. Well, so 3x cubed squared would be 3x to the power of 6, right?
That would be 9x to the power of 6.
Oh.
This last part would be 6x cubed plus 4. We had difference of squares, the regular factoring, and then square of sums. Right after school, if you want to come here, I'll give you half an hour, 45 minutes, but come right after school, please. Okay? Any future questions?
Are you free now?
I am.
So it's only
Yeah. Shoot. I have like 4 kids coming to make up a test, so we just have to be quiet. So they're going to be in here this period. As long as this room is open.
Just a quick question. I have to go to lunch.
What do I have? Okay, what do we have?
Yeah, you're good. This room is open. Tristan, go ahead. So this is like just more of a complicated problem, difference of squares, you know?
Will we see stuff like this on the test?
I mean, you should be able to do stuff like this. And the thing you want to recognize right away is that the middle term here, the middle symbol is subtraction, which means difference.
Right.
And isn't this something squared?
Oh.
And isn't this something squared?
Yeah.
So this is analogous to the following. How would you factor that?
X is 3x minus 3.
Easy, right?
Yeah.
Isn't that simple when you do it that way? It's the same thing. But again, think of this whole thing as the x. Think of this whole thing as the 9. So to get this parentheses here, you took the square root of this and put it here, right? You took whatever was being squared and put it here. So this whole thing is being squared, isn't it?
So take an x.
It's going to be really actually much longer, I need more room. And take this whole thing. Again, remember this x was being squared, so that became there. This whole thing is being squared. So this whole thing is going in for that right there.
So I would take x to x squared. So it'd just be the same thing, but just without the parentheses and the exponent on the outside.
And then
Subtract
after that,
and y.
add and subtract it to the remember earlier up here, we then took the square root of this and added that there, right?
Right.
And this came from this really, isn't it?
Oh wow, yeah.
So this is really 3 squared. So we took the 3 and put it there. We take this whole thing, which is squared, take this whole thing and put it in there. That's one of your factors. So if you think about it, right, this is like saying again, x plus 3. The x comes from here. Well, this is like your x plus 3. Where does that 3 come from? It's this quantity squared. That was this 9 squared.
Oh.
You'd have to do the whole thing again with this whole first term and then a minus sign here and this whole second term here. See what I'm saying?
Yeah.
So it just becomes messy. It's like, let's see, so we end up getting,
It's just the same thing. You just
but it is
take
difference of
opposite.
square.
Yeah.
It's just that this is your
I
base.
didn't see that.
And remember, whenever you do these problems, what do you have to think about right away? This is really x squared minus 3 squared, right? That's what you're thinking about. This goes here, and this 3, it goes here and here. Well, these are just two things that are squared and subtracted. This is squared, isn't it? And it's subtracted.
Right.
So it's difference of squares. It's just a lot more complicated.
Okay.
Okay, you should be able to do like most of the basic stuff, but also things like things that say, you know, like say you had something like this. And we did some of these in class, like that. That should jump out at you right away because all the numbers are squares, right? So what does this become?
5. And then that's 7 over 8
And variables?
x
Let's make this to the fourth, or to the sixth actually.
5x and then 5x minus and plus.
And what about the other part?
Oh, and then it'll be y to the third or y to the third.
Okay. So you should definitely be able to do that. These ones, like this one that you did in the homework, in the problem set, was just like more of a challenge problem.
Okay.
Okay, it'd be a bit longer, but you should understand it still, the concept.
Yeah. I looked at that and I didn't see like
That it was squares.
Yeah, I think
Mhm.
it's 2 squared.
That happens sometimes. That's okay. And a couple of those problems on the problem set were like that, where like even grouping wasn't obvious. Some of them you could have done by factor by grouping.
Right. Yeah.
You coming after school today?
I think I am.
Okay.